In this video we're going to look at the sampling distribution of the proportion and some miscellaneous pieces of information. So recall that a sampling distribution is the distribution of a statistic, of some characteristic from a sample. So how would one build a sampling distribution of a proportion? So you would select a random sample of given size. You'd calculate the proportion of cases with some given characteristic. You would plot this proportion, and then you would repeat the first three steps an infinite number of times. Or, in real world, we'll use statistical theory rather than repeating infinitely. I don't want to spend a lot of time on theory pertaining to the sampling distribution of P, that is, of the proportion. Small p signifies the sample proportion, large P signifies the proportion in the population. So, characteristics of the sampling distribution of small p. Its mean equals the proportion in the population from which the sample is randomly selected. Its standard deviation, the standard error of the proportion, is given by this formula. So the standard deviation of the sampling distribution is found by taking the population proportion, multiplying by 1 minus p, dividing by the sample size, and finally taking a square root. And then the third point is that as sample size increases, the shape of the sampling distribution of the proportion approaches that of a normal distribution. Now, in real-world research, we don't know the standard error of the proportion, and thus we estimate it using the sample proportion. So the estimate is the sample proportion times 1 minus the sample proportion, divided by the sample size, and finally taking a square root. Now, if both n times p and n times 1 minus p are greater than 10, the confidence interval for the proportion will be sufficiently accurate. And by that I mean if both of these are the case, these formulas below will yield accurate confidence intervals for the population proportion. And I will just make a side note. Sometimes sample proportions are very small or very large. For instance, a proportion might be 0.01 or 0.99 or 0.005 or 0.995. The proportion might be very close to 0 or to 1. So the text has a note in there pertaining to this situation. And if you get to a situation like that, then this guideline doesn't apply well. So I'm just going to say you should not use these formulas when the sample proportion is very extreme, such as just described. What is a 95% confidence interval of a proportion? It is the interval within which one is 95% confident that the population proportion is located. And here are two equivalent formulas for the confidence interval of the proportion. So let's proceed with an example, and again we'll use our statewide database of child maltreatment reports. So as presented in Chapter 12, in a random sample of 100 cases selected from this database, 40% of those cases were abuse cases rather than neglect cases. So then what is the 95% confidence interval for the proportion of abuse cases? So the first thing we need to do is check to see whether n times p and n times 1 minus p are sufficient in size for the formula to be accurate. So n minus p computes to 40, n times 1 minus p computes to 60, so therefore sample size is adequate to use the confidence interval formulas. So our first step in calculating the confidence interval for the proportion is to estimate the standard deviation of the sampling distribution of the proportion, which is to say we need to calculate that estimate. And you can see that the sample proportion is 0.40, that being the proportion of cases that are abuse cases. 40% of cases is a proportion of 0.40. So we multiply times 1 minus p and divide by 100 and then take a square root. So the standard error of the proportion, which is to say the standard deviation of the sampling distribution of the proportion, is estimated to be 0.049. And you know that's a very good estimate because we met this criterion. Both n times p and n times 1 minus p are greater than 10. We next multiply times 1.96, and this yields 0.096, and the final step is adding and subtracting from the sample proportion. So the sample proportion was 0.40, and so the 95% confidence interval for the proportion of abuse cases ranges from 0.304 to 0.496. This being so, we interpret and we can be 95% confident that the proportion of abuse cases in the full database falls within the range that spans from 0.304 to 0.496. I mean, that's our 95% confidence interval. Oftentimes, when we're dealing with proportions, we convert to percentages. So the 95% confidence interval for the percentage of abuse cases spans from 30.4% to 49.6%. We are not going to demonstrate calculation of the 99% confidence interval of the proportion. That is, of the interval within which one can be 99% confident that the population proportion is located. But here are the formulas, and note that the formulas use 2.58, whereas the formula for the 95% interval uses 1.96. So, I mean, just as is so for confidence intervals for means, confidence intervals for proportions are wider, which is to say less precise when we calculate 99% confidence intervals as contrasted to 95% ones. And indeed, this holds true, other things being equal in all situations. So we want to wrap up Chapter 13 at this point. And, I want to note that you have probably heard the term margin of error on television news reports. You've probably heard the newscaster say the percentage who support Obama is 46% with a margin of error of 5%. So I want to point out that margins of error and confidence intervals are different ways of expressing the same information. So as a for instance, each of the following expresses the same information. Suppose you had a confidence interval that spanned from 40% to 50%. Well, that's really the same thing as saying the margin of error. And if one wants to be technical, one can say the margin of error with 95% confidence is 45% plus or minus 5%. So the plus or minus 5% is your margin of error. But margin of error and confidence intervals are presenting the same information. Now, I want to note that the formulas presented in this text should not be used when the study sample represents more than about 10% of the population. So, for instance, if you have a study sample of 100 and a population of 500, then the study sample is 20% of your population. 100 divided by 500, 20%. That's an example of a situation where the formulas presented here should not be used. Chapter 13 has a footnote to help you deal with that situation. But on the other hand, if you had, say, a sample size of 100, selected at random from a population of 1,000, then that 10% guideline would be met, and these formulas will be sufficiently accurate. So in this third point, I'm presuming that the sample does indeed represent less than about 10% of the population, because you shouldn't be using these formulas if that's not the case. Now, given that that's so, I want you to see that it is the size of the sample, not that of the population, that determines the width of confidence intervals for means and proportions. Recall that n occurs in our confidence interval formulas, and n is the sample size. We have no term in our formulas for the population size. So it is the size of the sample, not that of the population, that's driving the confidence interval. Basically, if for you to get a confidence interval in a given range for a proportion or for a mean, and you have two situations. In one situation you have a town with 10,000 people. In the other situation you're dealing with the entire United States population, 300 million people. Well, you need the same size sample to generate the confidence interval in each of those situations. And this is not to say that it's as easy to take a random sample from among 300 million people as it is to take a random sample from 10,000, but you need the same sample size. If you get into very specialized survey statistics, you'll see some subtle differences, and the footnotes in Chapter 13 speak to some of these. You need to recognize that non-response can introduce bias. This bias is called non-response bias. So for instance, if we have presumed, in essence, we've presumed that 100% of persons have responded in all of our examples. But if perhaps 50% respond to your survey and 50% do not, then a big problem has to do with the notion that there may be systematic differences between respondents and non-respondents. So that perhaps you're asking about satisfaction with agency services. You have, in essence, no way to know whether those who respond hold similar opinions to those who do not. All you've got is data on respondents. So all of these confidence intervals are basic. In some sense, they're assuming a 100% response rate. And you do need to be alert to the fact that non-response can introduce bias. And fancy survey research pollsters do some things to try to reduce the bias that comes from non-response. And a final point is that at least through Chapter 13, but basically for the full text, this text is only calculating confidence intervals for means and proportions. But confidence intervals can indeed be calculated for all kinds of statistics, and they're very, very helpful. So for instance, perhaps the correlation in a random sample of, say, 200 cases between number of visits to elderly person in a nursing home setting and depression is, perhaps that correlation is minus 0.30 in your sample. A negative correlation. Well, there are formulas that allow, and indeed software programs easily compute confidence intervals. So I'm just pulling this off the top of my head, but perhaps the confidence interval in that situation spans from 21% to 39%. So that would tell you that, assuming that it's a 95% confidence interval, that you can be 95% confident that in the full population, the correlation between amount of visiting and depression level is somewhere in the range of minus 0.21 to minus 0.39. And I guess I'll sneak a sixth point in here, a basic one, but I mean, clearly these confidence intervals are applying to the population from which the sample has been randomly selected. So you can't do a study at, for instance, the University of Oklahoma and calculate a confidence interval. Well, indeed, you can calculate that confidence interval, but obviously you can't extend that confidence interval to, say, the University of Nebraska or even worse, to the University of Texas. And indeed, a final mention, perhaps a seventh point, do note that confidence intervals can only be calculated when one sample is a random sample. So that wraps up Chapter 13, and we are on now to statistical significance testing, the theory and background for which are presented in Chapter 14.